Okay. Fine. Maybe wait a little more, 1 or 2 minutes, so just begin. Okay, maybe just begin. Fine. I don't expect any more people to come in. Anyway. Okay, fine. Okay, the time is near 2 p.m. and let's just begin. So, Arendelle-ftl, and this is a QFT seminar just for fun. Remember, it's just for fun. Just enjoy it and just think it, just regard it as some playing a game or something else. Just a student seminar. Don't introduce any pressure or anything related to pressure. No need to that. Just for fun. Okay, so it's a QFT seminar, and my name is Ting Long Feng, and I'm a second year master student of theoretical physics at Utrecht University, and here is student QFT seminars. So I'll just simply introduce the reference textbook first. Reference textbooks we will use in this seminar. First is the QFT from basic to modern topic. From basic to modern topics by the Professor Jellis. Okay. And he's a professor based at Paris Saclay, I think. Yeah. This is the main reference textbook. The second one is QFT, a guide for mathematicians. Mathematicians. It's a book written by the Professor Folland. He's professor based at the Washington University at Seattle campus, I think. University of Washington, Seattle. Yeah. And the schedule. Every Wednesday afternoon from 2 p.m. to 3 p.m. 30. And today the first one, and it has the form of online. Yeah, the first one is today, November 19th. So we have an online form. And I made some minor change to my original schedule because I think it was taking more time to talk about something, the introduction part in some stuff in the chapter 1. So today I will only talk about the scalar field and put the perturbation theory to next time. Yeah. Stage 1. I think I will conclude the seminar as the LSC reduction formula, but let's see. Okay, the second seminar, November 26. Well, the schedule is the perturbation theory and QED. The initial schedule, okay. Theory. Corresponding to chapter 2 of the Jellis textbook, and QED. Chapter 3. The third one will perform. No. Okay. It's was scheduled on December the 3rd. The topic will be a very quick introduction of path integral. Notice here, I will not include anything about the quantum effective action or the two-particle irreducible formalism. I will just give a very quick introduction of the path integral for scalar field and spinor field vector field. Okay. 6.3, and maybe some initial part of the chapter 7 non-abelian gauge symmetry. symmetry. So this one may be part of. We may not. Maybe we cannot complete it in the third and the fourth seminar. We are scheduled in December 10th. The rest part, well, the plan is to perform the rest part of chapter 7 plus the chapter 8, the quantization of Yang-Mills theory. 8, yeah. And the last session before the Christmas break is scheduled in December 17th. It will be a talk about the quantum effective action and the RG theory, which corresponding to 5.5 to 5.6, and chapter 9 and 10. 9 and 10. Okay, and it will be a talk hosted by Alexander Godwitsky, not by me. Godwitsky? No. What will I write his name? Okay. Okay. Here is the basic schedule of this semester, and we may revive this seminar next semester, but we can talk about this later. Okay, so for today's topic, today is the first session of our seminar, and I want to talk about the scalar field. Okay, so I think everyone have learned something about the quantum field theory. So we all know the scalar field operator can be written as this: by x equal to d3p 2 pi 3 2ep, and combine the creation and the annihilation operator. Px. Okay, so I think we are all familiar with this this expression. However, when I first see such an expression in all the quantum field theory textbook, I'm a little confused, such as I don't know where does this stuff come from. Well, I know this, and I know it's just satisfying everything we need, such as the commutator relation, and we can define the conjugate momentum, construct the Lagrangian, blah blah blah. We can do everything using such an expression. But I'm still confused. I'm still curious about where does this one come from? How can we construct it in maybe a more rigorous way, I suppose? So the first part of today's seminar is such a try. I will try to introduce a relative rigorous construction about how we can obtain such an expression. Okay, the main content of the first part is based on the chapter 5 of the second reference book. Yeah, this one. Yeah, you can check. You can, if you are interested in today's topic, you should check this chapter 5 of this textbook. Yeah. Okay. So let's begin. Let me see the time. Okay. Okay. So first question. So what is QFT? In the most simple way to understand this, yes, QFT is a framework to unify the quantum mechanics and special relativity, right? So before we start into our topic, we must introduce a notation of the special relativity, such as the Minkowski space. Okay, Minkowski space. P space. These are just the normal notation in the special relativity, such as the 4 vector x0 xi equals to 1, 2, 3, and this x0 time component is just a ct, right? And of course, the for momentum, yeah, and some minor notation such as the partial derivative, mu, and some abbreviation, partial square, is just a Laplace operator, partial 1 square. Well, okay. And of course, the inner product in the Minkowski space, we can write it down as the x square equals to matrix G mu nu, x nu, or just x mu. Yeah. And notice that the metric we use is positive minus minus minus. You must notice it because it's very important. If you change to another metric, it will affect the properties of Fourier transform, and it will lead to many problems if you are not very careful. Such as if you were for later seminars when we compute the Feynman propagator for spinor field, if you use another metric, you must change some properties of the Fourier transform, such that you can obtain the correct result. So it's very annoying. And remember, we use this positive minus minus metric. Okay, and of course the Fourier transform in our Minkowski space definition is below. Fp equals to integral d4x eipx fx. Okay, and of course the inverse transform. Maybe I should change the notation. No. Okay, the inverse, no. Inverse Fourier transform. Okay. Integral d4p 2 pi to 4 power e minus ipx fp. Yeah. Okay, that's the notation we need from the special relativity theory. Okay, so if we want to construct a unifying theory, a unifying framework to or unifying quantized theory such as compatible with the special relativity, we must use the special relativity principle, which is that the physical law will not change in different inertial frame of reference. So, for example, if we observe a particle at rest in one frame of reference, xi, x0. Here is particle. It just no. Why it's just so ugly? Okay. Okay. So it's a particle at rest. Yeah. If we observe it in another inertial frame of reference, such as for example, we can make a rotation. Xi prime. Okay. X0 prime. Then the particle will perform a uniform linear motion, right? So, but actually they are the same. The physical law will not change because actually the rest state is equivalent to a uniform linear motion. Yeah. So how do we describe such a transformation between the different inertial frame of reference or Lorentz transformation? Well, we introduce the so-called Lorentz group. Lorentz group, which will be denoted by the orthogonal rule 013. And for any the properties is below. So properties are shown below. For any transformation in such a transformation group, we have the following property: ax mu, ay mu. Okay, equals to x mu, y mu. It actually doesn't change. Such a transformation doesn't change the inner product in our Minkowski space, and that's why it's called the orthogonal group. Okay. However, actually the group is too large for our usage because we don't want some component in such an the complete orthogonal group 013. For example, we don't want the reflection x minus x2 x change to minus x. Well, the change between the different inertial frame of reference we don't require such a reflection, so we don't want this. And So we add a restriction of such a group, such that we require the determinant of A equals to 1. And if we add such a restriction, the new group we obtain is called special orthogonal group 013. S013. It's the first restriction. And the second one is from the physical reality, we must preserve a time direction, right? Direction. Because of course we cannot come back to the future, obviously. So we require the sign of S00. A is not S0, A00 equals to 1. And with this restriction, the new group is called OL13. Yeah. And so we make some intersection between these two groups, and we obtain the group we will use in the whole quantum field theory, which is called the proper Lorentz group or restricted Lorentz group, which is denoted by SOL13, equals to the intersection of SO13 and OL13. Yeah, that's the group we will consider later. Okay. So we obtain the transformation group to describe Lorentz transformation. And because the special relativity principle requires us to consider requires the physics law, the unchangeability of physics law between different inertia frame of reference. So we must find an invariant space under this transformation group, invariant space. And we can do every analysis technology or analysis. We can use any analysis tool in such a invariant space, such as the Fourier transform and so on. And this in group theory, this place is called the orbit. Yeah. So we should find the orbit space of the proper Lorentz group SOL13. And it's actually relatively easy to perform it in the momentum space, and we can just write the 4 orbit space down simply as xm plus equals to p. Use coordinate maybe. P square equals to m square. Okay, for p0 larger than 0, and x minus x minus equals to p. P0 equals to M0, P0 less than 0, okay? And Ym equals to P. P0 equals to minus M square, P square, for M larger than 0. And the fourth is just the 0 space, okay? And we call the first two the mass shell. And in physics theory, we will only use the first two orbit space, I think. Okay. Notice that if we set the m to 0, the mass shell will become the x0 plus, x0 minus, and it's actually it is indeed the forward and backward light cones we encountered in special relativity theory. Backward light cones. Okay. Okay, great. So, how do we express the element in such an orbit, such as remember we are in momentum space, so for p in xm plus, how can we express it? And there's a trivial way to write it down, to write the p as the ep p, and introduce such a relation ep equals to square root m square plus the momentum square, the 3 momentum square. Yeah. Okay. So that's how we write an element in this orbit space. And next step, we must find the invariant measure on this orbit space because we want to perform Fourier transform and other analysis tool. So invariant measure. Yeah, invariant measure of the invariant measure on the mass shell. I think every physics student can do it in 1 or 2 minutes. We use some tricks, so I just write it down very quickly. After first we construct a function fp square dp4. Obviously, this one is the invariant in the Minkowski space, and because we require it obey the the measurement was defined on the orbit, so we just make the f to the delta function delta p square minus m square. So no, I don't like the new version of notability. Okay, delta p square minus m square, d4p. Yeah. And just using some basic properties of the delta function, delta p0 square minus m square as the 3 momentum module square, dp0, d3 momentum 3. And we just use some basic property of delta function, delta fx equals to delta x0, f prime x0. And x0 is the 0, it's just the 0 of the fx function. Yeah. And we can easily obtain delta p0 minus square m square dp0 d3 p momentum over 2p0 absolute value or module. I think I should use module. And actually, we can see that this one is just 1 over 2 EP. Yeah, so the invariant measure we obtain is simply d3, 3 momentum over 2 EP. That's the invariant measure we'll use later on such an orbit or mass shell. Okay, and we have obtained the proper Lorentz group to describe Lorentz transformation or transformation between the different inertial frame of reference. But now we still need, but if you want to complete physics 3, we still need the we still need something to describe the space and time translation. And for that purpose, we introduce the so-called Pangara group. A definition is really simple. It's just the semi-direct product of R4 and Lorentz group 013. And group law can be written down very easily, such as for any A and B in R4, S and T in this Lorentz group 013. We have the following group law as B T equals to A plus capital S B and capital S capital T. And the inverse element AS is actually minus S minus A and S minus 1, S inverse. Okay, and for any X in R4 space, the transformation law is a capital S, X equals to capital X plus A. So we just denote the space and time translation in the element using such an maybe R4 space or something like the addition group. Yeah. And of course, if you want to restrict to the proper Lorentz group, we will obtain the proper Pangara group P0 equals to R4 semi-direct product of the proper Lorentz group SO arrow 13. That's the group we will use later. Okay. Thanks so much for the transformation group and group theory. Now that let us come back to a very basic question, which is what is the elementary particle? Check the time. Okay, time is good. What is the elementary particle? Okay, so recall the special relativity principle. If we observe the same particle or the same physical interaction in different inertial frame of reference, the physics law should not change. So how do we describe it in the quantum theory? Well, in quantum theory, we describe quantum states using the Hilbert space, right? So such as we can introduce two Hilbert space, H prime and H. Related by some Lorentz transformation, and for the quantum states, V prime in the H prime Hilbert space, and V in the H space, and T the transformation element in the P0 group. Okay, so if the physical law will not change, then we must preserve the inner product of such a state vector. So these two state vector V prime and V must be related by a unitary map of state space. And if we write it down, it should be like this: UT V. Yeah. And here, this UT is just a unitary map of space of the state space. Of the state space. Okay, and obviously we will obtain the following property of this U map, which is UT1, UT2 equals to UT1, T2. Maybe with another phase factor. Yeah, it's just a phase factor. It doesn't matter. And actually, in the representations theory of group, we know something satisfying this is actually the projective unitary representation of the transformation group. So this UT is actually the projective unitary representation of our proper Pangara group P0. Okay. And using a theorem developed by a mathematician called Bergman. We will not get into the mathematical details. I just want to state it. Okay, if you are interested, you can check the mathematics books. According to such a theorem, we know that every projective unitary representation of P0 corresponds to a irreducible unitary representation of P0's universal cover. Irreducible unitary representation of P0's universal cover. About what is universal cover, I will not explain. You can check it in the mathematics books because it's not a point in the physics subject. And this one the mathematicians give us is just the G equals to R4 semi-direct product of the special linear group 2C. And we will come back to this one in our later discussion about the spinor and vector field. Okay, so much for this. So we have talked about so much about the group, the representation theory of group. So what the hell is the elementary particle? Just consider one simple fact that if you observe a photon in one inertial frame of reference, and you change to another inertial frame of reference, the photon will never change to an electron, obviously. And the same applies to if you perform a time or space translation one kind of particles cannot, one kind of elementary particle will never become another kind of elementary particles. So actually, so based on this fact, we just introduced such a definition of elementary particle that every elementary particle corresponds to a kind of irreducible unitary representation of such a P0's universal cover G. Okay. And for example, for a scalar field, we will discuss later, which corresponds to the maybe Higgs bosons. The scalar field or the scalar particle just correspond to the trivial representation of such a group, of such a universal group G. Scalar field. A trivial representation of such a group. And of course, for photon, later we will know it's correspond to a four-dimensional representation, but it's not today's topic. Okay. Okay, so much for this. Maybe not this line. Okay. Okay, now we can construct the free scalar field. Free scalar field. Okay, 30 minutes. I think I can do the first part in 15 minutes. I hope, hopefully, free scalar field. Okay, first, just recall the famous Klein-Gordon equation. How can we obtain it in a very simple way? Well, just recall the energy momentum's relation, P square equals to M square, right? And perform use a Fourier transform, I partial mu, and we can simply apply obtain this one, partial square, M square, F equals to 0. And here, this F we call the classical field. Field. And we need to quantize it. We need to quantize such a classical field. So how do we do it? How do we deal with such a problem? We can start from the single particle state, Hilbert state, single particle state. State space, Hilbert space H equals to L2 space M plus lambda. Notice this S2 L2 space. If you're not familiar with definition, you can just check any introductory functional analysis textbook or the functional analysis for physicians and so on. Simply speaking, it's just the module square, the basic integral space, functional space. Something like that. Okay, I don't actually as we physicians don't I'm not so concerned about the rigorous definition of such space. And for this lambda is a normalized measure. We can express it like this. P over 2 pi to 3 power in P. Okay. Okay, and recall some basic knowledge in quantum mechanics, or I should refer to the second quantization maybe, or some other names. We have learned famous for the boson-Fock space. Space. H. Okay, and the corresponding annihilation and the creation operator, which denoted by A and A dagger. And of course, the basis of the space, EJ. And I will just write down the definition quickly of such operator, AJ 1, J square and J 1. nj minus 1. This is the annihilation operator and the creation operator. 1 j equals to square root nj plus 1 and 1 j plus 1. Okay, and of course we have the commutator relation AW W equals to VW I and AW. The commutator between the annihilation and creation vector, creation operator. It's just simple relations. And of course, if you introduce a unitary map, unitary operator on a unitary operator on the Hilbert space H, we can induce some transformations such as we can induce a transformation in the Fock space, and with a simple operator corresponding to AV and AV dagger. It's just the basic group transformation theory, not group transformation. Just the basic transformation theory. Okay. Okay, so that's what we have learned in the quantum mechanics. Now we want to quantize the classical field we mentioned before. How do we do it? First, we define a map, mapping from the Schwarz space to the Hilbert space, which will make an F to its make it become this Fourier transform defined on the mass shell. If you don't know what Schwarz space is, you can check the some introductory functional analysis or distribution theory book. Equals to its Fourier transform restricted in the mass shell XM. Yeah, and I will write the Fourier transform down explicitly. IPX fx dx. Okay, and now we can define the quantum field, but it's not the ultimate expression. We will counter quantum field. Yeah, field capital psi as a map from the Schwarz space to an operator on the Fock space. Yeah, I can just write it down something like this. This A and A dagger are just the creation and annihilation operator in the Hilbert space in the states in the Boson Fock space we have introduced before. Yeah, and notice that this phi, this capital psi f, no, the capital phi f is actually a distribution solution of the Klein-Gordon equation. Solution to the KG equation. You can just check it very quickly if you perform the partial square. You will obviously obtain 0 because partial square m square f. You make a Fourier transform together and restricted in the mass shell. You will obtain this one. And it obviously vanished. So this quantum field, the capital phi f, is actually a distribution solution to the KG equation. Okay, but now what we want? We want something like this, field operator defined on the R3 space, right? So we want to obtain this one. So how do we do it? How do we deal with it? We introduce a unitary map we introduce a unitary map. Mapping from the L2 space on math shell to the L2R3, the space we are concerned. So we can just write it down. UP equals to 1 over square root EP U P. Okay, and using the induced transformation we have stated before, we can obtain the transformation under such a J of the creation and annihilation operator, and of course, the quantum field capital phi. We equal to J minus V, J minus 1. Yeah, and this V are the element in the L2R3 space. And similarly, we can write down the A dagger, and of course, the phi f, capital phi f, fj verse. Yeah. Okay. And notice that these two operator, we can regard it as the operator valued distribution on R3 space, and using the standard definition of a distribution or the generalized function, we can just write it down as this in this way. AV, no. R P3 T. In such expression, obviously these V are just the test function, and this AP are just the annihilation operator in the momentum space. Yeah, and similarly, we have the A dagger. Yeah, we have the A dagger. AP dagger, VP E3 moment 2, 5, 2, 3. And we can easily check the commutator relation of the AP and AP dagger. It's just the 2 pi to 3 power delta P minus Q. Okay. So on the final step, we just combine everything. Phi f equals to 1 over square J dagger J inverse. And just substitute the every expression we have obtained before. JRF as the dagger JRF. And notice that this argument JRF is actually 1 over square root EP, the Fourier transform F P just equals 1 over square root EP integral 1 EIPX FX dx 4. Finally, we can write down the ultimate expression of such a distribution defined on the L2 R3 space phi f x d4x. 1 over square root 2 EP minus IPX. The annihilation operator. Yeah. IPX. The creation operator. Okay. And actually this one in the box is a phi x we want, just like the in the beginning of our seminar we mentioned. Where is it? Yeah, just this one. No, I don't want this. Yeah, just this one. You may notice that these factors are different, but it can just change easily by introduce a new definition of the annihilation and creation operator, such as you can just change the AP to AP over square to EP, and you obtain the phi x, which has the same structure of the expression in every textbooks. APX, APX. Okay, so that's the first part of this seminar. Okay, exactly 45 minutes. I think it's good. And let's have a 10 minutes break.